Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss that what is the viscous force acting on a cylinder which is moving inside a long pipe, and that pipe is containing some liquid whose layer is very thin and it is bounded between that moving cylinder and the pipe. So you can see that there is a long pipe whose length is L, and L is very greater than radius of the cylinder, and radius is very greater than the thickness of the oil. So the thickness of the liquid, viscous liquid or oil, is very low, and hence we can say that the velocity gradient will be constant. Now the scenario is this, that we have initially given some velocity v0 to the cylinder, and then we are not applying any force continuously on it, and hence it would eventually get slowed down, and eventually the cylinder will come to the rest. So we have to find out the velocity of this cylinder as a function of time. So for that, let us first of all discuss about the velocity gradient. So we can say that as the thickness of the oil layer is very small, so the velocity gradient will be almost constant, and velocity gradient will be equal to v naught by, in fact, v by z, because at any time t, at any time t, the velocity will be equal to v, which would be less than the initial velocity. So the velocity gradient will be v by z, because the points which are in contact with the inner wall of the pipe will have zero velocity, and the points which are in contact with the cylinder will have v velocity at any time t. So the velocity gradient will be equal to v by z, and the viscous force acting will be equal to neta into area, which is, area will be the curved surface area of the cylinder, which will be 2 pi r l, and velocity is v by z. So this will be the viscous force, and this viscous force will be equal to ma, and a will be minus of dv by dt. So it is 2 pi r l neta into v by z. So we can say that dv upon v will be equal to 2 pi r l neta divided by m, and this is z also, so it is dt, and integrating both the sides, the limit of v will be from v0 to v, and the limit of time will be from 0 to t. So ln v by v0 will be equal to 2 pi r l neta by mz into t with a negative sign, and the value of v will be equal to v0 e to the power minus 2 pi r l neta t by mz. So this will be the velocity of the cylinder, and the variation of this velocity with time will be obviously exponential, and this would be like this. And the total heat generated will be the initial kinetic energy. So total heat generated will be equal to kinetic energy initially, because eventually all the kinetic energy will be lost. So we can say that the total heat generated will be equal to half m v0 square. Okay, so this is this simple case, but in this case, in the second case, when the layer of thickness or layer of oil has non-negligible thickness, which means that we cannot neglect that thickness, and the inner radius or the radius of the moving cylinder is r1, and the radius of pipe is r2, and r2 minus r1 is not negligible, and we are continuously applying a force F naught on the inner cylinder, and due to this force this inner cylinder is moving with a constant velocity V naught. This is constant, and we have to find out the velocity at any point which is at a distance of r from the axis of the common axis of the cylinder and pipe. So in this case, obviously we can say that velocity gradient will not be constant, and we can write down that velocity gradient will not be equal to v naught minus 0 by r2 minus r1, because this oil layer is not negligibly thin, so we cannot say that velocity gradient will be v naught upon v naught minus 0 upon r2 minus r1. This is wrong. So let us suppose that at any distance r from the axis of the cylinder there is a small thin cylinder whose width is dr. This is a cylinder. I have not drawn the complete surface, but this is the thickness of the cylinder. So the velocity of this point, inner point of the cylinder, will be v, and the velocity of the outer point will be v minus dv, because this velocity will be decreasing, obviously. Okay, and obviously we can say that the velocity gradient will be equal to dv upon dr, and the viscous force acting will be in the backward direction, and this viscous force will be minus neta into area, which is 2 pi r l. L is the length of the cylinder, into velocity gradient is dv by dr. And as we know that velocity is constant, because v is constant, because v naught is constant. So all the layers will be moving with the constant velocity, and hence the net force will be 0 on each cylinder. And we can say that the viscous force will be equal to the external applied force F naught. So F naught will be equal to minus neta into 2 pi r l into dv by dr. Okay, and now we can say that again we are writing down the same expression, that F naught is minus neta into 2 pi r l into dv by dr. So we can say that dr by r will be equal to d, in fact this is minus 2 pi neta into L into dV divided by F naught, and integrating both the sides. So we can apply the limits that at the inner cylinder radius r, small r is r1, and the velocity is v naught. So we can say that at r is equal to r1, v is equal to v naught, and at the internal wall of the pipe velocity is 0 and the radius is r2. So at r is equal to r2, velocity will be 0. So this is ln r2 by r1, and this is equal to 2 pi neta L by F naught into V naught. Okay, and this is the first equation. Now if we apply the limit of dr by r from r1 to r, and here it would be 2 pi neta L by F naught, and the limit will be from V naught to V. So it would be ln r by r1, and this will be equal to 2 pi neta L by F naught, and this will be V naught minus V. Okay, so if we divide these two equations, so we can say that dividing one into ln r by r1 upon ln r2 by r1 is equal to 1 minus v by v naught. Okay, so you can easily see the scenario, and here we can say that v by v naught will be equal to 1 minus ln R by R1 upon ln R2 by R1. So V by V naught will be equal to, taking LCM, so ln A minus ln B will be equal to ln R2 by R upon ln R2 by R1. So V will be equal to V naught, and this is ln R2 by R upon ln R2 by R1. So you can check the expression also, that at R is equal to R1 at the inner cylinder, this will be equal to V will be equal to V naught, and at R is equal to R2, V will be equal to 0. So this will be the correct answer, and this is the velocity at any distance r from the axis of the cylinder. In the next video, we are going to use this expression to find out the Poiseuille's equation, in which we would find out the volume rate flow through a pipe. Thank you.